Yeah, well, I forgot my iPad, so I got to.
That's all I had to say.
So it was like a Monday all day long. Okay. So let's chit chat about let's just start with the spring problem. How about that? So
That's all I really have to say about that.
you've got this uncoiled spring, right? And it's 4 centimeters long, and you hang it down, you attach the mass, you can draw a graph of force and elongation. You're going to find your spring constant because you start at 0, 0, and you got 1 point. So if A is wrong, everything else is going to be wrong. So your spring constant.
It's your Pocket Lab thing from Harbor Scientific.
Is what?
Your Pocket Lab thing.
Oh, okay. Oh, cool.
Yeah, now that I have to put all that in, all of it comes to me, so I guess.
Oh, so you get to play Santa Claus.
Yeah,
Gotcha.
not what I was going for. It's good to see all the
Okay.
people.
Okay, so that spring constant should be around 1 Newton per meter. Okay, because if that's wrong, it's going to be a train wreck from there on out. So you have 2 forces involved. So then you're going to put this charged beads on each end, right? And it's going to stretch it out. So basically the force that it's going to take to stretch that spring is equal to the repulsion between the charged particles, right? Just set these two equal. So you know your spring constant, you know this. Now, here's what you have to watch. That value of x is what the elongation is. It's how far it stretches. It isn't the length of the spring, okay? So you have to be careful about that. So if you notice, it says that this causes the spring to stretch to a new length of 4.5 centimeters. So don't put in 4.5 centimeters from there. It's going to be how far it stretches. This distance here, though, this distance is the distance between the beads. Okay? That is the distance between the beads. So if all goes well, your answer to B should, in nanocoulombs, should be between 30 and 40. Like that answer? If you don't, you did something wrong. Okay. So, very, very likely you will see a question like that on the test tomorrow. I'm just saying.
As long as
Not
it's not
completely
letting.
certain, but more than likely.
As long as it's not protected.
Okay. Now, let's talk about this on that multiple choice question where you've got like the 3 charges. You've got negative Q here, positive Q here, 2 charge Q here, there's your origin. And you got negative R, 0. Okay? So, basically, what I did when I wrote this is I took you through the thought process you should go through to arrive at your multiple choice answer. Okay? So, one of the first things you have to remember or figure out, are you asked to find the force or are you asked to find the field? Okay? Because they're related, but they're vastly different things. So, on this one, you want to find the electrical field at the origin. So you want to find the net electric field right there. Now, here's the deal. Think this through. Could I even ask you to find the force on a particle here? Do you have enough information? Lauren, you shake your head no. Why?
I just don't think you. I don't know. I don't know.
What do you
you
have
have the
to
radius.
have to calculate a force?
You don't have the radius.
You got to have 2 charges, right? Because it's KQ1, Q2 over D squared. So I couldn't find the force acting on a particle here if I tried because I don't know what the charge is. Okay? I don't know what that is. That's the whole point, is that I don't know what that is. okay? See the difference? So I can't, now if I said, oh, there's a charge of positive 3Q here, then I could ask you to find the net force acting on it, okay? But I can't calculate the force here because of the fact that I don't know what that charge is. So this is a situation where you go, okay, hey, I'm just going to put a positive chest charge here and see what that effect is. So remember, if you calculate force, that's K Q1 Q2 over D squared, okay? Now, how do you calculate the electric field? What's one way to calculate the electric field?
Force equals EQ.
K Q over R squared. Now, here's the question. Is that charge the one that you're detecting, or is that the charge that's creating the electric field?
Creating.
That's the one that's creating the electric field. Thank you. Hand that to Kelsey. I'll let you get done. I'll let you know when it's convenient. But remind me to let you know that when it's convenient, or otherwise I'm going to forget this thing. Now, what's another way that, what's another equation that involves force, a field, and a charge?
Force over.
Effect, right? Or E equals F over Q, okay? It's another one. So, if you think about it, this makes sense, because if you look at this in terms of, if you were to solve this for Q, that'd be F over E. So, or if you look at this in terms of just this, so if you know what the electric field strength is, and then you plug in that charge, then you know how much force is going to act on it. So clearly, the stronger the electric field is, and the bigger the charge is, the more force that's going to experience, okay? All right, so the whole key to this is going to be the sign. So I want to make sure everybody's cool, starting off right on this one. So on this one, you got to determine the electric field created by Q directed towards O. So on this one, here's the origin. So that's just going to be KQ over R squared. Now, which direction is this field going to point? To the right? Or if leave out these two, leave these out. Okay, those have nothing to do with it. You're just focused on this. So if you have a positive test charge right here, this is going to be the value of the electric field, right? KQ over R squared. Well, which direction is it going to point? To the right or to the left? If I put a positive test charge right here, okay? If I put, and I'm talking about, says on number one, determine field created by the positive Q directed towards O. So if I put a positive test charge right there, it's going to feel what?
Ripples.
And it's going to tend to go in this direction. So that electric field, this is that answer. Okay, that's what I want for number one. And it's going to be a positive value because that field is going to be pointing in this direction. Okay, so this is it. This is all you have to have. Okay, make sure though, understand why it's positive, because it's going in that direction. Okay, cool with that. All right, now when you get to 2Q, so 2Q is going to be over here, right? Now what do you got? So if I put a positive test charge here, what's it going to feel? It's going to feel force in this direction. But now that's going to have a charge that's going to be twice as much. Okay? But it's going to be going in this direction. So I've got one going this way, and then I've got a 2Q going this way. Then look at it in terms of what's going to happen with that negative Q. So what you want then, on number 4, what I want is that you're going to say, okay, here's the sum of my x components here's the sum of my y components. Do not just write down, oh, here's x and here's y, okay? Make sure that you put down what is what. Okay, just don't write down two numbers and expect that I'm going to know what they are. And then, what you're going to see, then you're going to make, basically you're going to make a Pythagorean, you're going to do the Pythagorean theorem. So you're going to have some x component, you have y component, find that hypotenuse. And your answer is not A. How about that? It'll be on the lower half. How about that? Okay. Now, here's the question about on that question on the back side, and I promise you there's going to be a question like this. Make sure that you realize that we're talking about the electric field. What I would recommend is you start with vectors and you point them in different directions to see what's going to point where. Okay? And your answer on that one is not E. How about that? I help you. Okay. Are we good with that? Okay. Cool. Good. Okay. Now let's talk about the assignment. Because I want to make sure kind of everybody knows what's going on in that assignment, because that's going to be a lot of what the test is going to be. Let me see. So on 52, which is kind of a cool one just because it's a theoretical because you've got a proton. So your answer on 52 as a decimal, as a meter, should be like 0 point something. Okay, it might start with a 1, I'm not sure. Okay? I'm just saying. Maybe, maybe not. But here's the whole key to this, is that the two forces, and I promise you, there's going to be a question like 52 or 54. I promise you, where you're going to set these forces equal to each other. Okay? I promise you. Now, on 54, what's your net force going to equal?
0.
Why?
Yeah, it says that it's 0. I was going to say.
Net force is 0. So what are the two forces that are involved?
Positive and negative.
You have the two different forces, right? So you have KQ over D squared. So here's what you want to look at in terms of distances. So because it's D squared, okay, anytime you have something with D squared, if you double the distance and somehow or another, you know, a factor of 4 is going to be involved. Okay? It's either going to be a fourth as much, it's going to be 4 times greater, it's going to be something. So anytime you see a doubling of a distance, you know a factor of 4 has to be involved. On 56, again, that's one of those big complicated ones where you've got to find the volume, and then you got to use that to find the density, or that you're given the density, and then you've got to go through and find the number of charges and all this good stuff, because it's a carbon atom, it's 6 protons. So if there's some little like checks along the way, so your charge, okay, total charge should be something around, the total charge should be something around 0.06 coulombs. Okay, so that's the total amount of charge. Okay, something around there. So then, as a fraction, then that fraction on 56, because it asks for a fraction, should be 1 over and then maybe something around 30-ish. Okay, if you reduce that down. Because it asks for a fraction. Now, on 60, I like 60, because you got to go old school. So if you look at what's happening on 60, so you've got these plates, and they're separated by 1 millimeter. So you can use a little feck, right? And then the first thing you've got to find is that electric field. So you've got a Q over epsilon naught A, okay? So pay attention to the units. So because if 6A is wrong, everything else is going to be wrong. So your answer to 60A should be something times 10 to the 6th newtons per coulomb for that electric field, okay? Pay attention to the units and how you calculate that area, okay? So that answer on 60A should be something times 10 to the 6th. So it's 10 to the 6th. So then on B, you're going to use feck. You're going to find the force, and then you can find the acceleration, and then eventually you have to go old school and use that equation, V naught squared plus 2AX. So you're going to find your force. You're going to go F equals ma. You're going to find the acceleration. Boom. Put that in there. So if all goes well, your velocity should be something times 10 to the 5th meters per second. And I promise you there's going to be a question like this on the test. I promise you. Okay? So your answer to 60B should be something times 10 to the 5th meters per second. And you should get a really big acceleration. Like your acceleration should be something times 10 to the 14th. It's not your velocity, that's your acceleration. Okay, I like 62 as well. Okay, so that's where this thing is hanging out at a 45-degree angle. You got to find your weight. So on 62, your charge in nanocoulombs should be between 5 and 10. Okay? So on 62, it should be somewhere between 5 and 10 nanocoulombs. Got that? Anything else you want me to go over? Now, if you want to hold on to this and hand it in tomorrow, that's cool. If you're feeling good about it and you want it, and you're done, and you can hand it in, and I'll grade it. It's up to you. You can hand it in today. You can hand it in tomorrow. Whatever works for you. Because this is what a lot of the test is going to be like. Okay, so I'll just leave that up to your discretion. All right. If you want to take a picture of it so you have it and then hand it in,
I'm going to
you want to kind of click over it.
Yeah, I think we're wrong. We discussed this for hours over candlelight.
We've written essays about it. It's going to be my thesis for my graduation.
Yeah, we use Mrs. Pfeiffer's signature Socratic.
Just stop.
We got a Socratic.
Yeah, go ahead and stop. Okay, so we're going to go over this, but this is kind of like, there's just two problems. This front side's obviously much more complex. So you got two small objects, you're given the charge, held together by a length of string. Objects are visibly rest on a horizontal, I like how they go through this whole thing. Horizontal, non-conducting, frictionless surface, okay? Because what happens otherwise, people get nitpicking, oh, there's friction and all this other stuff. Anyway, so you want to calculate the tension of the string, otherwise known as tension means the same thing as force, right? So obviously, since there's tension in the string, what's the only way that can work is if the two charges have, yeah, either both positive or both negative, okay? Otherwise, they were oppositely charged. Illustrate the electric field. Remember which direction field lines are going to point, because you have a negative charge. Then you've got the masses of each one. Calculate the magnitude of the initial acceleration of each object. And then you're going to sketch the acceleration as a function of distance, and then describe qualitatively what's going to happen. And then there's a multiple choice question on the back. So I'm going to give you about 5-10 minutes. Work through that, and then we'll go over it.
That's what I got.
3.6.
10 to the negative 4.
Beautiful. Okay? Now, in this situation, by the way, Buddy's up, camera going. Okay. In this situation, they both have the same amount of charge. Okay, they're both negative 4 nanocoulombs. Let's play the what if game. What if one had been negative 4 nanocoulombs and one had been negative 8 nanocoulombs? Okay? If that were the case, which one would experience the larger force? The negative 4, the negative 8, or would they both still experience the same force?
The same.
They would both experience the exact same force. Okay? Because it's just like the analogy of here's the Earth and here's the Moon. Earth obviously has a lot more mass than the Moon does, right? But they both are going to feel the exact same gravitational force. Okay? So if the charges So even if the charges had been different, they still would both experience the exact same amount of force, just like the Moon and the Earth both experience the same gravitational force. Okay? The Moon accelerates more because it has less mass. Okay? But they're both going to experience the same gravitational force, doesn't Newton's third law. Okay. So what'd you get for the different accelerations there?
0.012.
What'd you get? Point
012 for the first one, and then 0.006 for the second one. Sorry.
0.006?
Yeah.
So which one is going to have, which one has the bigger acceleration? The smaller mass or the larger mass?
Small.
Yeah, because they're both going to have the exact same force, but then because it's the same force divided by mass, boom, that's going to give you your acceleration. Okay, so you got that one. Now, on B, here's what I would want on B. So here's your charges. Now, which direction are the field lines going to point? Because these are negatively charged particles. So which direction are the field lines going to point? Of course. Now, this is, and again, there's going to be questions on that lab as well, okay? So, is there a point, okay? Because remember, voltage equals KQ. Okay, we'll talk about voltage, because voltage is the energy in the system, okay? So, is there a point in between where there is no electric field?
Yes.
Where's that going to be?
In the middle.
No. So so if you put a positive test charge right here, what's direction is it going to go?
It's nowhere.
Right? If you put one here, what's it going to do?
Nothing. Oh wait.
Right? So what I'm looking for on your field lines is something like this. Okay? Now, is there a point in the middle where your voltage can go to 0? No, because this is KQ, right, over R. So if you look at this in terms of KQ over R, because of the fact that both of these are negative values, what you're going to find in the middle is a very, very large negative voltage in between the two of them. Now, if you had a positive and negative charge, then could there be a point of no voltage in the middle?
Yes.
That could happen, okay? That could happen. Because you would talk about the sum of those. So you could have no voltage in the middle if you have opposite charges, but could you reach a point where you have no electric field in the middle if they have oppositely charges? No, because if you put a positive test charge here, what would happen? It would get repulsed by the positive, and it would get pulled towards the negative. So on oppositely charged situations, you can have no voltage, but you always have to have a field. If you have two like charged particles, you can reach a situation where you have no field, but you're always going to have a voltage. So that was one of the things you worked through on the second page of that lab that I just gave back. Okay? So make sure you understand what's happening between positive and negatively charged particles in terms of fields and voltages, or if you have two positive or two negatively charged particles. Okay, so you got that. So what does your graph look like? So you have acceleration here, distance here.
Would it be a straight line? Because, oh wait, I had it as a swoop, but then I was like, wait.
Buddy, do you have something like this?
Yeah.
Yeah, okay, as long as it's something like that. So why does your acceleration become smaller and smaller and smaller?
It's distance squared.
Because as you get further and further away, what happens to the force? It becomes smaller and smaller and smaller, so your acceleration, so eventually your velocity time graph would become like a horizontal line. So theoretically, no matter where you go, there's always some acceleration, but effectively it would like drop to zero. Okay. So then on E, what happens to the speed of the object as time increases? So here's what you should say, something like this on E. So they're not talking about acceleration, they're talking about the speed. So you would say something like the speed increases dramatically at the first, but then like the rate of change in your speed becomes smaller and smaller and smaller until your speed basically becomes constant. All right, so what do you have as your answer to the multiple choice question on the back?
B.
What'd you say?
I said B.
Beautiful answer.
I figured if you drew it kind of like a vector thing, you got 3 units, 1, 2, 3, then 1,
That's what you
2,
got.
then you draw your resultant, and then boom,
Yeah.
it looks like B.
It is. So, huh? What? Okay. So you've got negative Q, 2Q, positive 3Q, and then Q. So if you go do exactly what Gannon said to do, okay, it was a beautiful answer. So you're talking about the next direction on Q, right? And again, now here's what's different. Why can you talk about the force,
Two charges.
Gannon?
Because, it's newtons per coulomb, and you know that this is 1 coulomb, so, yeah, force.
Two charges.
Because you
Two
have all
charges.
your
Because you have all the charges.
Yeah.
That's the answer. Okay? Now, in this situation, riddle me this. If I asked you to find the field at Q, could you talk about the field at Q? Would that be any different than the force at Q? Well, let's get the force down first, right? So, what's this one going to feel in terms of this charge right here?
attractors.
All right, so it's going to have an attractive force down like this. Now, if this was a test charge, would that electric field point in the same direction? Yeah, the electric field, if this was just a positive test charge, and I said, figure out the net field at this point, that would point in that direction, right? Okay. Now, what about this one? What's going to happen here? In terms of the force. You got a positive Q here and a positive 3Q there. So what's it? It's going to try and do what? What's it going to try and do?
Go away.
It's going to try and drive it up like this. Bigger or smaller than this one?
Bigger,
Bigger. Why?
greater charge.
It's got a bigger force, right? Bigger charge. So then if I take this and do like a little tip to tail method and draw that result, then that's why you get speed. Okay? Now, if you were talking about the electric field strength, okay, would that look the exact same way if it was an electric field strength? If I just said, what's the net electric field up there, would that look the exact same way?
Yes.
Yes, because they're both based upon a positive test charge, right? Now, if this had been a negative Q, then the force in the electric fields would look completely different. Because if that had been a negative Q, right, then let's play the what if game. If that had been a negative Q, this would drive it this way, this would drive it down this way, and it would point in that direction. So if that had been a negative charge, the field and the force wouldn't be the same. But since that's a positive charge, the field and the force both end up with the same thing. Okay? That's what you have to be careful with. All right. Okay. Let's talk about voltage and how that relates to gravity. All right? So let's say that I've got like a positive and negatively charged surface. So let's say that I've got a balloon and I charge it up. So this would be like the surface of my balloon, and then this would be the surface of the blanket. Okay? So I've created this disturbance, right? So I have a negatively charged region and a positively charged region here. Now, let's say that I had an electron right here. Would I have to put energy in to move it towards the negatively charged plate?
Yes.
Why?
No.
Yes, because they're repelling.
So you have two things going on, right? Does the electron want to move towards the negatively charged plate?
No,
No. Why?
because it's
Negatively charged.
Same
Yeah.
charge, right?
and it's attracted to the positive.
And it's attracted to the positive, like, oh man, this really sucks, okay? It'd be bad enough if you just had a negatively charged plate up here. So if you look at this voltage, because remember, what are the units for voltage?
Joules per coulomb.
Joules per coulomb. If you're not sure, what are the units for K? Newtons?
I literally cannot remember them for like. They're not on the sheet.
Newtons meter squared over
Coulomb squared.
Coulomb squared, right? And then if I multiply that by Q, I get coulombs, and I divide by meters, right? Okay? So then that's going to cancel out that's going to cancel out one of those. I get Newton meters per coulomb. Newton meters are the same thing as joules. So that's joules per coulomb. So look at this. So the farther that I push this thing, okay, so if you look at KQ over R. So if you look at this in terms of voltage, voltage is the measure of like how much energy there is per unit of charge. So if you were to look at this in terms of like lines, you could have lines of equal potential going across here. So if I put an electron at any point in between there, it's going to have that same amount of energy going up. So these lines of equal potential, because I'd have to do work. I've got to lift this thing up because it's attracted towards the positively charged and it's repelled by the negative. So I have to push really hard to get this thing to go up there. Now, if you look at the Earth, okay, so you can model the Earth in a gravitational field in a similar type of way this is. So if I have a 1 kilogram mass and I lift it up, well, that's going to have a certain amount of energy, okay? You can think of it as like joules per kilogram. And the higher I lift it, right, I'm going to get more and more and more potential as I lift this thing higher and higher. But I have to do work. So these lines of equal potential energy here is the same concept as you lifting an electron up here. So you would have lines of equal potential energy here. Instead of joules per kilogram, you would have joules per coulomb. But these lines would be parallel with the surfaces, just like there would be, you know, the same idea of the Earth. So that's the analogy. Now, if I drop this thing, what's it going to go?
Fall to the Earth.
Fall. Why?
Because it's attracted, or Earth is attracting it with its gravity.
Yeah, and it's going to go to a lower energy state. Okay? Same thing is going to happen here. If I lift that electron up and let go of it, what's it going to do? It's going to fall back down because it's going to go back to a lower energy state. Okay? Now, visualize this. Speaking of electrons, instead of going that way, let's see, we gotta remember the numbers. Okay. I do kind of like writing on the board, though. This is like, I feel much more like I'm like teaching.
Do you have any chalk? That'd be
Oh,
cool.
that's what I would really, you know, that's my old school goal, is to get like an actual chalk. The really cool ones, I don't know if you've seen them. In the big lecture halls, they were like on pulleys, and you'd have like 3 or 4 of them, and you could lift them up and down. Oh. Okay, you still my beating heart. Okay. So, visualize this. And you all have actually done this problem very similar, okay? Back when you had the acceleration and projectile motion test, okay? You did a problem like this. So, but before I gave you the force, now you're going to find it. So here's the deal. So you have 2 parallel plates. One's positively charged, one's negatively charged. You have an electric field. Now let's talk about the electric field. What's the direction of the electric field in between the plates? Does my electric field point up, or does my electric field point down? Why does it point up?
Positive test charge is away.
Because the positive test charge would do what? Go up this way. So the direction of my electric field is going to be pointing up in this direction. Okay, so that's one of the key things you've got to be able to do, is find the direction of the electric field in between parallel plates. So, that's the strength of my electric field. I got an electron shooting through. The length of this plates are 12 centimeters, about like yay. The electron enters the field at 5.8 times 10 to the 7th meters per second, pretty close to the speed of light, not quite there, but pretty close. So what I want to know is, how much does that electron, how much does that path get deflected? Go. So, Carter,
Comes closer, the force is going to increase.
okay,
Yeah, we took spring break, all the knowledge was just thrown out.
Oh,
I don't know
fantastic.
about that. I don't know.
I mean, there wasn't a lot to begin with, but like.
Oh, no.
Yeah, no, I took a-
Thank God I didn't have to
Well, I
today.
don't think it matters because look, you,
Yeah.
so 120% to
So look,
4
you can go F equals X, right? You have an electron, so you know the charge on the electron. You know the electric field, you can find the force. Now, which direction is the force going to act? Upward, so this is like upward gravity, right? So if I take this marker and I throw it to Diego, right? So why did it only accelerate vertically when it left my hand?
There's only vertical gravity.
That's the only direction there's a force, right?
Yeah.
So is there any force acting horizontally? No. So is there going to be any acceleration horizontally? No. So what can you use when you have constant velocity? What's the one equation you can use when you have constant velocity?
Force.
Huh?
That means
What did you just say? What did you say?
Don't worry about it.
And the
Just keep
viewer?
going, just keep going, it's fine.
What did you say?
I'm not telling you.
Did you say F equals MA? You are so bright red right now.
Don't worry about it.
Distance over
Just keep going,
time.
it's fine.
Right?
Yeah.
Yeah, F equals D over, or
Right,
D equals D
D over
over T. V equals D over T.
D over T.
Y
Yeah,
equals
yeah.
mx plus v.
Distance equals velocity times time, right?
Yeah, that's
It's the only time you can use this. When you have,
Constant
velocity.
One.
do you know how far it travels with this velocity?
Yeah.
Yes. Can you figure out how long it takes for it to go through there?
Yeah.
Yes. Would that be the same whether there's an electric field or not?
Sure.
Yes, just like if I threw this to Diego and there was no gravity, it would still take the same amount of time to get there. Because what happens in the X
Stays in
stays in the X. What happens in the Y
Stays in the Y.
stays in the Y. So, you know your force, you can find your acceleration, and then you can do 1/2 AT squared plus V naught time. Now, what happens in the X stays in the X. What happens in the Y stays in the Y. Vertically, this is where your acceleration is happening. Is there any initial vertical velocity? No. Don't take that and put that in there, okay? So, you have to figure out how long it's here. There's your time. F equals ma, there's your acceleration. You can figure out how far it's going to get deflected. Now, Mr. Carter, stop that, and then you all figure it out. Okay, so what you get from the value of the force that the electron's going to experience?
2.88 times 10 to the negative 15.
What'd you get, 2 point what?
88 times 10 to the negative 15.
Times 10 to the negative 15
Yeah.
newtons, right? So you took the charge on the electron, 1.6 times 10 to the negative 19, times the value of that electric field, that's the force that it's going to feel. Now, if it had been a proton, well, let's go back to the electron. So when this electron enters this field, is it going to be deflected up, or is it going to be deflected down? Party girl.
Can you repeat the question?
When this electric field, when this electron goes between these two plates, is it going to be deflected up, or is it going to be deflected down?
Down,
Why?
because it's negative, and it wants to go to the positive, but it's repelled by negative.
Okay. So if it's a negatively charged particle, it's going to go through here something like this, right? Hold towards the positive, repelled by the negative. If it was a proton, would a proton feel the exact same amount of force?
Yes.
Yes, because it's 1.6 times 10 to the negative 19th. So a proton would feel the exact same amount of force. But, what would be the path of a proton?
Go up.
But would it be symmetrical to this, but just pointed up?
No.
Which, would it be deflected more, or would it be deflected less?
Wait, yeah, less.
Less,
'Cause it
why?
weighs-
Why, Miss F equals ma?
Hey, because it has more mass.
With the same force, therefore it's gonna have a
Smaller.
smaller acceleration.
Because F equals ma.
Because F equals ma.
It's the only thing I know.
Yeah, it's the answer to everything. F equals ma. Now, would a proton or an electron take longer to travel through the field?
Proton. Wait.
Same
Oh,
velocity,
yeah. Then,
time's gonna be the same, right?
Yeah.
If it's an electron or a proton, they're both gonna take the same amount of time to go through. So time's gonna be the same. Okay, so what did you get for your time?
2.07 times 10 to the negative 9 seconds.
Okay? So you took the distance of 0.12 meters and divided that by 5.8 times 10 to the 7th meters per second. And you got what?
2.07 times 10 to the negative 9 seconds.
Okay, not very long, right? Now, here's what you're gonna do wrong. You mark my words. You're gonna flip this over, and you're gonna take meters per second, you're gonna divide it by meters, and you're gonna get a really, 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 really big amount of time.
I did that and I was like, there's no way that's possible, so I fixed it.
Yeah, because that would be like, an orbiting satellite has like 10 to the 3rd seconds. Okay, this would be like 10 to the, 8th seconds, okay? So realistically, probably not gonna happen. Now, so now I've got my time, right? So now I just need my acceleration. So here's my force. If I take that force and divide that by the mass of an electron, what's the mass of an electron?
9.11 times 10 to the negative 31st kilogram.
Negative 31st kilograms. So I'm going to take this force and divide it by that mass, and then what do you get as your acceleration?
3.16 times 10 to the 15th meters per second squared.
Now, if it had been a proton, what would happen to that acceleration?
It'd be smaller.
It'd be smaller because a proton has a lot more mass, okay? If it had been a neutron, what would happen?
It would be
Nothing.
smaller.
Same thing.
Nothing.
Oh, wait.
Why?
Because it's got no charge.
It has no charge, right? Okay? So this is why neutrons were so very, very difficult to find. Because if you shoot a proton through, it shows up. Shoot an electron, and this is basically what J.J. Rutherford did, is that he had the beam of electrons, and he put them on a positively, negatively charged plate. And he saw how they were deflected. They were deflected towards the positive and away from the negative. It's got to be a negatively charged particle. Ernest Rutherford did the same thing with alpha particles. Okay, so he figured out those were positively charged particles because he sent those through an electric field, and those were deflected up, but not near as much as electrons were deflected down. So that's how he figured out that they're positively charged and they're much more massive than an electron is, because they don't get deflected as much. Okay, so now you have all the numbers to plug in here. So what did you get as your deflection? So you got distance,
0.00677 meters.
okay, so a little scientific notation.
So 6.77 times 10 to the negative 3rd meters.
And if you put that into millimeters, that would be
6.77 millimeters?
6.77 millimeters, okay, which would be about like yay, okay? Give or take. So, if it had been a proton, if you look at this calculation, if it had been a proton, the time would have been the exact same, the acceleration would have been
Less.
Less, so your deflection would have been less, okay? We got that. Okay. See, why was that so bad?
No, it's not as, okay. When you say lemming problem, I think of when the process where you have to find the way up, find that time, find the way down, find that time, like add
And
it
that's
together.
basically
That's
what
not
we
even
did.
that
We're
hard.
shooting a lemming through the electric.
Yeah, but it has the same velocity, so you don't have to worry, like, you don't have to, there's less to worry about.
It reminds me of the bear
Those
problem.
lemming problems were
Okay.
all day,
The bear
I
problem.
The
thought.
bear problem.
Oh no, never bring up the bear problem ever again.
I like that bear problem.
Yeah, well, that bear problem can stay in first
Yeah,
semester,
but this isn't
so.
even relative visible.
How about this? I promise you I don't give you a bear problem.
Thank God. Watch you rephrase it to be like a wolf or
Where's the election,
something.
huh?
A proton is electron, electron is
I don't feel.
a proton comes.
That would be the moment that I would I'd walk out. I'd be done. If I saw that on like the final or something, I'd be out.
You'll do it. And then
Oh my God, here, Bodie. Scholars Bowl.
Yeah, this is for
place.
state, and then this is for league. We
Oh,
got first at league.
so easy.
Our only loss was to Mesa.
if I had
Oh,
It was Joel.
sorry.
That was just
So I just.
I'm gonna say
In my 2 days of solder points, because I was passing.
We want it. We want like 5 into the.
He's a controller. And I flipped it off. So it's I did not show that.
Okay,
What is this?
so, a similar type thing, okay?
That's not.
But yet, it's more complicated to get less complicated.
that's just.
So, you have two plates. All I'm telling you is that the electric field is going in this direction. Okay, that's the direction of the electric field. I'm going to release a proton here with an initial velocity of 4.0 times 10 to the 6 meters per second. This is the direction of the electric field. It's going to travel 30 millimeters across this plate, okay? I want to know what the velocity is when it hits over here. So, let's start at the beginning. It's a proton, right?
Yeah.
Okay? So right away, you know you can use FEC to find the value of the force. So this is where it's similar, right? Once you find the force, what else can you find?
Acceleration.
You can find the acceleration. So if I take force and divide it by mass, I can get my acceleration. Now here's the million-dollar question, okay? Here's the million-dollar question. The proton released like this, right? The electric field is coming across like this. So here's the question. As it goes across, is the proton going to speed up or slow down?
I'm gonna say slow down.
Adam Buer,
I don't know.
what did you say?
I didn't say anything.
Yes, you did.
No, I didn't. I said.
You did.
Did
You
you say
said slow
ethical
down.
No, I
MA
didn't.
again?
That was me.
Oh, you said it. Okay. Joelle, why is it going to slow down?
Because if the electric field is going this way, then it's attracted to the negative charge, so the negative has to be on this side.
Okay? So think this through.
Doesn't that mean
It's
that
nice.
it's
Okay, hold on. Let's leave everything else out of this. Okay? If the electric field is going in this direction, is this plate over here positively or negatively charged? Negatively charged? And this side over here would be? Because if I put a positive test charge here, okay, then it was going to be pushed away from this and it would be attracted towards this. So that means this side over here is positively charged, this side over here is
Negatively charged.
negatively charged, right? So if that's the case, then as this proton is shot going across like this, is it going to speed up or slow down as it goes across? It's going to slow
Down.
down, okay? Because it's losing kinetic energy and gaining potential energy, okay? That's one way to look at it. It's like you're shooting it up a hill. So, you have a distance and you have an initial velocity. What are you going to use to find the final velocity?
B squared equals B naught squared plus
That equation.
2A.
V naught
X
squared
minus-
plus.
2A.
Now, here's what you have to think through though. Here's my initial velocity, right?
Yeah.
I got the distance, right? But what sign do I have to make my acceleration?
Negative.
Negative, okay? So you would just have to think it through in the context of the problem and make that a negative value. Now, if the electric field had been going in this direction, would it experience the exact same acceleration?
Yes.
Yes, it would experience the exact same acceleration,
But it would
but
be
if the
positive.
electric field was going this way, what would it do?
It would be positive.
Then it would speed up, okay? So, you're gonna use Thec, force divided by mass, get your acceleration. That's what's going to go in here. But what you have to decide in the context of the problem, based upon the direction of that electric field, is it gonna speed up or is it gonna slow down? And you just have to decide to make that acceleration positive or negative within the context of the problem. Okay? Now, let's say that let's say this is a negatively charged balloon. Okay? And the only thing I have is a negatively charged balloon. I don't have the blanket. Okay? I only have the negatively charged balloon. What can I do to get these two spheres equally charged? Or can I get them equally charged?
Yeah, touch it together.
Hold on. So I touch these together, then what? So here's my negatively charged balloon.
Hold it up to me, not touch it.
Huh?
You hold it up to me, not touch it.
I bring it close, but do I touch it?
No.
So if I bring it close, this is a negatively charged balloon. What are the electrons on the first sphere going to do?
Go to the second one.
They're going to go over there, right? So what's that going to leave behind?
Positive.
Positively charged. So I bring it close, right? Then what?
Then you let go and they'll be opposite.
I separate them, then what?
They'll be opposite.
Then I pull this away, okay? All right? Now, in that situation, this balloon, or this sphere over here would be
Negative.
negatively charged, this would be
Positive.
positively charged. Now, if I touch them together, negatively charged balloon, and I physically touch the balloon to it, and then pull them away, now what's going to be the charge on each sphere?
They both have a negative charge.
Then they're both going to have the same negative charge. So keep track of what you do to have a negatively charged two equally charged spheres or two equal and oppositely charged spheres. Okay? Because that's one of the things that you've got to keep straight. Okay, we got 5 minutes.
That velocity did not slow down. It did not slow down. It did. We don't have practice. We don't have practice.
Okay. So let's say I'm going to give you a very small charged sphere. It's charged to negative 2 nanocoulombs. Has a mass of 3.2 grams. I want to find the strength and the direction of the electric field to make that thing hover. So in the name of time, take me through the sequence. What force do you know is going to be acting on?
Gravity.
Can you find the value of that force?
Yeah.
Yes. So that's going to be Fg equals mg. Clearly, that's going to be pointing,
Down.
so I got a gravitational field acting down, right? So if it's going to balance that out, what's going to balance that out?
Electromagnetic force.
Right? So can you do effect?
Yep.
Because you're going to know what that force is, right? You know this charge, right? So then you can find the value of the strength of the field. Now, here's the $1,000,000 question. Which direction does the electric field point? Does the electric field point down, or does the electric field point up?
Up.
Why down, Diego?
So it's momentum charged, so it has to point in the opposite direction or else it'll be attracted upward.
Yeah, because if you have your electric field pointing up, a positive test charge would want to go up, right? So a negative test charge would want to go,
Down.
so therefore my electric field actually, and that's counterintuitive, because you would think, oh, the electric field needs to point up. The electric field would actually point down. Okay, so those are the big ideas. You have all of your assignments back, you have all of your labs back. You're on your own.